The integrated circuit operational amplifier is the premier linear active device in present-day analog circuit applications. The device itself is a complex array of transistors, resistors, diodes, and capacitors, all fabricated and interconnected on a tiny silicon chip. I will now describe how a high-gain DC amplifier circuit can perform mathematical operations such as addition, subtraction, multiplication, division, integration, and other mathematical methods, hence the name operational amplifier. Before I discuss on developing a circuit model for the op-amp, let me first discuss some op-amp notation. The op-amp is a 5-terminal device, and let me draw that right now. So what we have for the symbol of op-amp is basically a triangle as shown here. It has 2 input terminals, one plus and one minus. The one associated with the plus is called the non-inverting input, and the one connected to the minus sign is a inverting input. We also have an output as a result of those 2 inputs. And then we have the power supply terminals. Top is usually reserved for the positive power supply, and the one at the bottom is the negative power supply. Since the op-amp is an active device, it requires power to make it work. However, when we draw these circuits, the positive power supply is usually denoted as plus VCC, and the negative power supply is usually denoted negative VCC. While some op-amps have more than 5 terminals, these 5s are usually present and are the only ones we will use in this series of tutorial videos. The 2 power terminals shown here are not usually shown in circuit diagrams. However, be assured that they are always there because the external power supplies are required for the op-amp to operate as an active device. The power required for signal amplification comes from these terminals from an external power source. The plus VCC and the minus VCC voltages applied to these terminals also determine the upper and lower limits on the op-amp voltage output. Okay, let's look at the op-amp voltage and current definitions. Associated with the input is the non-inverting and the inverting inputs. We have an IP going into the plus side of this op-amp, and that's again our non-inverting input current, and as well as our voltage measured with respect to ground, VP. Here we have our inverting input IN, and associated with it is our positive VN, also measured with respect to ground for the inverting side. And at the output we have VO, and associated with VO is our outgoing current IO. In addition, we have the currents and voltages due to the power supplies, one at the plus end and one at the minus terminal. So here we have IC plus denoting as the input current due to the VCC, plus VCC, and one due to minus VCC as IC minus. When we do a global KCL equation associated with the op-amp, that is the outgoing current is equal to the incoming currents. We have IO is equal to IC plus IC minus plus IP plus IN. Again, the outgoing currents is equal to the incoming currents. And we also note that the outgoing current does not equal to the 2 ingoing currents at our input terminals, IP and IN. Anyway, that because they don't include IC plus and IC minus, and that these values here, IP and IN, are usually small, that we'll see. In fact, we'll use this to define our ideal characteristics associated with an op-amp. Now let's look at the transfer characteristics of an op-amp. And what we mean by transfer characteristics is what's the output in terms of our input. Well, our input is in terms of our non-inverting and inverting inputs. In fact, it's the difference between these two inputs multiplied by some high gain. So this is very high gain. Very high gain. It's upward someplace 10 to the 6, a million. Okay? In fact, you can draw the characteristics associated with this in terms of a graph, where our input is the difference between VP and minus VN, and our output is result right here. So here along this linear region, this line is our gain. So our slope has a rise of A and horizontal run of 1. So in other words, the slope has a gain of A. And this is a very steep slope. As I mentioned before, it has a very high gain. Such a high gain that it saturates very quickly to our positive and negative power supply. In other words, you can't go higher than what you're supplying in terms of voltages. So our output voltage is limited by our plus VCC and minus VCC. And when they operate in this region, we call that the saturation region or mode. Here we call this the linear mode, so that a corresponding increase in our voltage difference between VP and VN is a corresponding increase in our output. So look at this ideal op-amp model. Again, we have VP and VN, our non-inverting and inverting inputs. And here we have an input resistance. Usually this is very high. We have at our output VO. And then we have a corresponding IO. So that we have our output as a result of the amplification, large gain amplification of VP minus VN. And we have our output resistance RO. Here I wrote down two ideal characteristics associated with an ideal op-amp when we analyze a circuit, and usually these are good approximations, such that VP equals VN and that IP equals IN equals 0. And we'll see why. First, let's look at VP equal VN. Since our output is VO and is a result of the application between VP minus VN, we have this relationship. But A, we can assume, is very large or infinite. When that's the case, VO divided by A is closely equal to 0. That's approximated, and that means that VP equals to VN. Since A has very high amplification again. Now IP equals IN equals 0 is a result that the input impedance here, Ri, denoted as Ri, is equal to a very large number. When that's the case, when this is, let's say our ideal case for this is infinite, then IP and IN is equal to 0, since no current can pass through this infinite resistor. So these are two ideal characteristics associated with the op-amp when analyzing a circuit. So to justify our ideal op-amp characteristics, let's look at some typical op-amp ranges. For the input resistance, right here, shown here, it ranges from 10 to the 6 to 10 to the 12 ohms. For RO, it's 10 to 100 ohms, so that's a very low value. So most of the voltage applied here, A times VP minus VN, is dissipated or is delivered as VO, where very little is dissipated as RO. And most important, our gain is from 10 to the 5th to 10 to the 8th. So these values give us a typical justification for ideal characteristics associated with the op-amp.